So hi guys, since we have already discussed about the moving coil instruments and the electrodynamometer type instrument, today what we are going to do is that we are going to look at two questions, two problems. So the first question here, let's look at it. Let's read the question once. So it's very important to understand the question, so only then you can you will be able to analyze, or you will be able to solve this question easily. So let's look at this question. So it's given that there are two ammeters X and Y have resistances of 1.2 ohms and 1.5 ohms respectively, and they give full scale deflection with 150 milliamperes and 250 milliamperes respectively. So you have X, let's write down side by side. You have X is an ammeter. It has a resistance of 1.2 ohms and it gives a full scale deflection. With 150 milliamperes. I hope you know what is full scale deflection, right? The last point in the scale. So the full scale deflection is obtained at 150 milliamperes. We have already seen all these things, because generally the full scale deflections will be in milliamperes, and then we extend the range by using shunt resistances. For ammeters and for voltmeters we use series resistance for increasing the range. So then there is another meter which is given as Y. It has a resistance of 1.5 ohms and has a full scale deflection of 250 milliamperes, right? Now the ranges have been extended. The next sentence says that the ranges have been extended by connecting shunts so as to give a full scale deflection with 15 amperes. So the ranges have been extended for both these instruments by giving shunts. So you can write it there. After using shunt, the FSD, full scale deflection, changes to 15 amperes, right? So that is the new full scale deflection after using shunt resistances, right? So if we can visualize these resistances, let's say this is X, this is the meter X, which has a internal resistance. The internal resistance is given by 1.2 ohms. Then you have a shunt resistance. We don't know what is the value of the shunt resistance yet. Let's call it Rx. Now it can take up to 15 amperes, right? But the meter can still take only up to 150 milliampere. So the purpose of putting a shunt is that all the other current apart from 150 milliamperes, whatever is the current, it can pass through this shunt resistance. So here in this case it would be 14.85 amperes, which is 15 minus 0.15 ampere, right? 0.15 ampere is passing in this branch, so the other branch will have a current that is 14.85 amperes at full scale. This is the full scale values. It is not necessary that always there should be a current of 15 amperes, but at full scale, this is the current that will pass through this meter, right? The meter will still take the same value of current, which is 150 milliamperes, but the shunt resistance will take all the other current. So in the case of Y, the same concept applies. So you have a meter which has an internal resistance, and then you connect a shunt resistance Ry, and the internal resistance is given as 1.5 ohms, right? Sorry, 2.5 ohms. So 1.5 ohms, 250 milliamperes, sorry, yeah, 250 milliamperes at full scale deflection, which is 0.25 amperes. So this meter is also extended by connecting a shunt to get a full scale deflection of 15 amperes. So the 15 amperes is the full scale deflection. So the rest of the current passes through Ry resistance, which is 14.75, which is 15 minus 0.25 amperes. 250 milliamperes is 0.25 amperes. So you'll get 14.75 amperes at full scale deflection. That's the maximum that you can pass through this meter, right? So I hope this much is clear. Then it is mentioned that, so this ampere came out at over here. Basically it is 15 amperes. It's not the meter, it is ampere. It should have been here itself, yeah, to give a full scale deflection of 15 amperes. The ammeter along with the shunts are connected in parallel and then placed in a circuit in which the total current flowing is 15 amperes. The current in amperes indicated by X is. So this is a very tricky statement. What they are saying is that the ammeters along with the shunts are connected in parallel and then placed in a circuit. So you have to understand what they are trying to say here. So what they are saying is that X and Y are connected, X and Y along with their shunts. So let's call this Rx, and the meter X, and you have the next meter which is Ry, and it also has a meter which is Y. Both these meters are connected in parallel. That is what they said. Both these meters are connected in parallel. So let's connect them in parallel and placed in a circuit. These meters are connected in parallel and placed in a circuit where the current flowing through the circuit is, the ammeters along with the shunts are connected in parallel and then placed in a circuit in which the total current flowing is 15 amperes, right? So the total current flowing in this circuit, so this is the circuit somewhere starting from this point, and there could be some other devices over here. So the total current that is passing through the circuit is given as 15 amperes. The current in amperes indicated by X is. Now in this case, what is the current that is indicated by the meter X? That is the question, right? I hope it is clear, because when you connect these two meters, the total 15 amperes will not pass through any of these meters. Instead, these currents will get divided and they'll pass through two different meters. I mean, some part of the current will pass through this meter and some part will pass through this meter. Basically what they are asking is what is the amount of current that is passing through X. So let's call this Ix and Iy. So our objective is to find what is Ix, what is the current that is going through this particular meter. Because this meter had a full scale deflection of 150 milliamperes, is now corrected to 15 amperes. So whatever current that passes through these two, the combination of Rx and X, will be read by this meter X, which should be definitely less than 15 amperes, because that is a full scale deflection of X. But in the circuit you can see the maximum current that is coming itself is 15 amperes. Some part is going to go into the Y meter, so therefore the rest of the current will only pass through X meter, right? So let's calculate this value. Now first what we'll do is that we'll first calculate what is the value of Rx and Ry in this case. So to have a deflection of full scale deflection at 15 amperes, what should be the value of Rx and Ry? So this can be done in different ways. Either you can use the current division rule. That is, what you will do is that you can give the equation for what is the current through this branch or through this branch, any of the branch. So what you will get is that, let's take the current through Rx. So if you are taking what is the current through Rx, you can write this equation as the total current, which is 15 amperes. 15 amperes is the total current that is coming here. Now 15 amperes into the opposite branch resistance. The opposite branch resistance is 150 milliamperes, which is 0.15 amperes, divided by it is not the opposite branch current, it is the opposite branch resistance. So the total current into opposite branch resistance divided by total resistance. So the opposite branch resistance is 1.2 ohms divided by the total resistance is Rx plus 1.2 ohms, which is equal to the current through Rx. The current through Rx we have already seen, that is 14.85 amperes. Now if you solve this, you will get that the value of Rx as Rx is equal to 0.01212 ohms. This will be the resistance of Rx for extending the X meter to a full scale deflection of 15 amperes. Now we'll find what is Ry. Now another method is that you can directly multiply. What you can do is that you can directly multiply these two values. Easiest way is 0.15 into 1.2. If you multiply 0.15 into 1.2, you will get some you will get the voltage in this branch, right? You will get the voltage in this branch. Now if you divide the voltage with the current of the branch, so in this branch means the voltage will be same for both these branches. So whatever is the voltage that is there in this branch will be same for the next branch as well, and whatever value you get, you can directly divide with 14.85. you will get the resistance Rx. So Rx will be equal to the voltage that you get over here. So let's see what is the value. 1.15 into 1.2, you will get as 0.18 divided by 14.85. You will get the same value. So here you will get it as 0.18 divided by 14.85. you will again get it as 0.012 1212. This is an easier way to calculate what is the resistance. Now similarly, if we calculate what is the resistance at Ry, you can find what is the voltage in this branch, right? That is equal to 250 milliamperes into 1.5. So 0.25 into 1.5, 0.25 into 1.5 will come out as 0.375. Now Ry is equal to 0.375 divided by 14.75. that is the current over here. So the answer divided by 14.75 will turn out as 0.02542. So you will get Ry as 0.02542 ohms. I hope the calculation is clear. If you are confused, you can go with the conventional method. You can directly apply the current division rule. So if you apply that rule, you will get an equation in the form 15 into opposite branch resistance 1.5 divided by Ry plus 1.5 is equal to the current that is flowing through Ry, that is 14.75, and then solve for Ry. You will get it as again the same value, right? So once you have found what is the value of Ry and Rx, and then we can look at this circuit right now. So here you can see that there is Ry and Rx. Now what you can do is that you can again apply the current division rule for these two resistances, and you can find what is the current that is passing through your X ammeter. So here Rx we have already found. Rx is equal to 0.01212 ohms. Ry is equal to 0.02542 ohms, right? Now what you can do is that you can find what is the total resistance of this meter. So if you want to find what is Ix, you will have to have the resistance of this meter and this meter separately. So let's say the total resistance of Rxt, let's call it Rxt, the total resistance, that is by combining these two resistances. So X meter has a resistance and the shunt resistance also has a resistance. Rxt will be equal to, you will have to apply the parallel rule. So that is 0.012 0.012 into 0.01212 into the meter resistance of X is given as 1.2 ohms. 1.2 ohms divided by 1.2 plus 0.01212. So you will get it as 0.01212 into 1.2 divided by 1.2 plus 0.01212. You will get the value as, when you calculate this value, you will get it as 0.0 0.1199 ohms, right? And for the total resistance of Y meter with the shunt resistance will come out as 0.02542 into 1.2 divided by 1.5 is the meter resistance. 1.5 divided by 1.5 plus 0.02542, R1 R2 by R1 plus R2. So you will get this as 0.02542 into 1.5 divided by 1.5 plus 0.02542. So this value will come out as 0.02499 ohms. So these are the two values of the resistances after combining the shunts. Now if you apply current division rule, you take 15 amperes and apply the current division rule. The resistance RYT divided by RXT plus RYT. So RXT is 0.1199 and RYT is 0.2499. So when you do this, you will get the result as 0.02499 into 15 divided by 0.02499 plus 0.01199. You will get this value as 10.13 amperes. When you calculate, you will get this value as 10.13 amperes, and this will be your result, 10.136 or 10.13 amperes. This will be your final result. So when you connect RX, when you have these connections in parallel, the Y ammeter and the X ammeter with their shunts, you will finally end up with this value of 10.13 amperes that will be detected by the X ammeter, and Y ammeter will be detecting the rest of the current, which is 15 minus 10.13 amperes, which will come out as somewhere around 4.87 amperes or 4.86 amperes. So that would be the current that will be measured by the Y meter, and the current that is measured by X meter will be 10.13 amperes. So this is a very good question. This was asked in GATE 2014. GATE 2014. So I saw this question, so I thought we can discuss this question in this video. We'll be discussing one more question today. So let's look at this new question, the second question. So let's read the question once. 2. The DC current flowing in a circuit is measured by two ammeters, one PMMC and another electrodynamometer type, which is connected in series. So there is a circuit, DC current is flowing through the circuit, and you have two ammeters. One is the permanent magnet moving coil and the other one is electrodynamometer type. Both are connected in series, and the PMMC meter contains 100 turns in the coil. The flux density in the air gap is 0.2 webers per meter square, and the area of the coil is 80 millimeter square. The electrodynamometer type ammeter has a change in mutual inductance with respect to deflection of 0.5 millihenry per degree. The spring constant of both the meters are equal. The value of current at which the deflections of the two meters are same is. So basically what we have is, we have two meters. One is a PMMC meter and the other one is a the electrodynamometer type meter, right? PMMC and electrodynamometer type meter, right? Some of the parameters of both these meters have been given to us, and sorry guys, and we are asked to find what is the deflection. So there is some current I that is passing through these meters, and we are asked to find what would be the current I, or let's say some current is passing. What we are asked to find what is the current I, capital I, for which the deflections of both these meters would be same. So deflections means the theta, right? Theta for both these meters will be same for what particular I? That is the question. Now it is also given that the spring constant of both the meters are equal. So let's write down the parameters. Let's write down the parameters for both these meters. So for the PMMC meter, this is a bit more direct question. So for the PMMC meter, given that N is equal to 100 turns, B is equal to 0.2 webers per meter square, area is given as 80 millimeter square, which is equal to 80 millimeter square can be written as 80 into 10 power minus 6 meter square. Millimeter square to meter square conversion, you will have 10 power minus 6, right? And then that's all that is given with the PMMC meter. And for the electrodynamometer type meter, electrodynamometer type meter, the values given are the change in mutual inductance with respect to deflection. Change in mutual inductance with respect to deflection, what is that? That is your dm by d theta. Change in mutual inductance, that is dm, with respect to deflection, that is d theta, is given as 0.5 millihenry per degree, can be written as 0.5 into 10 to the power minus 3 Henry per degree. Now let's look at what are the equations for the deflection, right? So in PMMC, the deflection angle theta is given by, theta is equal to NBA divided by K into I, right? Similarly, in electrodynamometer type meter, the deflection theta is given by, theta is equal to I square by K into dm by d theta, right? Now what are we asked? We are asked to find the value of current at which the deflections of the 2 meters are same. So what we have to do is that we have to equate these two equations, because the thetas and the deflections are same, means the theta of both these angles, both these meters should be same. For what value of current? That is the question. So let's equate these two equations. So you'll get it as theta is equal to NBA I divided by K is equal to I square by K into dm by d theta. In the question, it is also given that the spring constant of both these meters are equal. Both these meters are equal, which means that this K corresponding to PMMC and the K that is corresponding to electrodynamometer type instrument, both are same. So you can cancel these out, right? Both are on the denominator of two expressions, so you can cancel these out, because when it comes to the right hand side, it comes on the numerator, so that's fine. Now the n is given as 100 turns. The B is given as 0.2 Webers per meter square. 0.2 Webers per meter square. Area is given as 80 into 10 to the power minus 6. 80 into 10 to the power minus 6 into I is equal to I square into dm by d theta. Dm by d theta is given as 0.5 into 10 to the power minus 3. 0.5 into 10 to the power minus 3. Now here the question is, what is the theta, what is the current I for which the theta is same? So both these currents should be same, only then you can find what is the current I for which both the meters will give the same deflection. So you can cancel out these i's, so I and I square get cancelled, so you will have I remaining in the right hand side. And now we can solve for this I, because that is what is asked in the question. In the question we have been asked what is the current I for which both the meters will give the same deflection theta. So I is equal to 100 into 0.2 into 80 into 10 to the power minus 6 divided by 0.5 into 10 to the power minus 3. So here you can cancel these out. This will come out as 10 to the power minus 3, and if you solve for I, you will get it as, let's solve for the value of I. So you get as 100 into 0.2 into 80 into 10 to the power minus 3 will come out as 1.6 divided by 0.5 will come out as 3.2 amperes. So you will get it as 3.2 amperes. So 3.2 amperes is the current for which both these meters will have the same deflection. So that finishes our second question. So this question was also part of the GATE 2014 paper, 2014 paper. I hope you guys have understood this. If you have any doubts, you can message me. Okay then guys, bye.